Okay, so we're trying to get Moshe into the backstage of this event. Just give us a few seconds.
connected. Okay. I'm in. Choose camera. Okay. Can you see me now? Yeah. Okay, good. We can see each other. Can you hear me? Can you hear me on Clouder? Yeah. Can you hear me?
Yes.
Okay. Now, how do I share the screen? Share. Where is share screen?
The videos.
You're here. Happening now. Program verification. Share screen. Okay, good.
Okay.
But tab. No, it wants to share the browser. I need to close the browser. Hold on. The browser is dominant. I have to close the browser. Oh, it's a problem. Share screen.
Okay.
I may have just to share the whole screen. Okay, let's try that. Am I sharing the screen? Do you see my screen?
Yeah.
Not yet. Window. Okay, I think now it's going to work.
Yes.
Okay.
Because
yep, let's.
What I thank you very much for.
Okay, I apologize for the complexity of this interface. So I want to tell you today to offer a 70 plus, to be precise, 72 years perspective on program verification. And you can imagine if I try to squeeze 70 years into 1 hour, it's going to be very selective, and it's just my perspective of it. And I'm sure I would love to hear from all of you about what are the big things that I missed. So one of the early insights when you start programming, when I started writing my first program in Fortran, it's very hard to write error-free programs. And there is a long list of not just bugs, but very bad bugs. I mean, life critical bugs, property critical bugs, all the way from not intercepting Iraqi missiles to crashing the Mars climate orbiter, the Pentium chip. I mean, it's just a very, very long list. As far as we know, the first time that this was formally addressed was in a short paper by Alan Turing in June 1949. So 2 years ago, we celebrated 70 years anniversary of program verification. And it's a short paper in which he asks, how can one check a routine in the sense of making sure that it is right? It doesn't say what right means, but in intuitive sense, in order that the man, I don't know why only men, who checks may not have too difficult a task, the programmer should make a number of definite assertions, which can be checked individually, and from which the correctness of the whole program easily follows. And really what you find in that paper, this is from a later a review of the paper, the 3 pages of the text contain excellent motivation by analogy, a proof of a program with 2 nested loops, and an indication of a general proof method very like that of Floyd. So this is the first paper on program verification. Then there is a bit of hiatus from 1949. And the next time we find a paper which is not really about verification explicitly, but implicitly it is a paper by John McCarthy, 1963, called A Basis of for a Mathematical Theory of Computation, in which he does address the issue, how do we formally get formal properties of program? He was thinking about recursive programs. So he had to deal with not with loops, but with branching and with recursion. But again, we do find the basic idea, a very early idea on how to reason about programs. When it comes to receiving the Turing Award, this work was not mentioned. It was mentioned only his contribution to artificial intelligence. Then we jump a few years and we find Peter Nohr, another Turing Award winner, in which he described a proof of algorithm, not program, algorithm by general snapshots. But again, if you look what are the general snapshots, again, these are essentially assertions that you put on the state of the, you call it expression of static condition existing whenever the execution of the algorithm reaches particular point. So again, it's a method of assertions. And again, this did not make it into his Turing Award citation, which was mostly again for programming language design. But again, you find the same idea that goes back to Turing. And then we find it more explicitly, probably the most evolved is by Floyd, 1967. And so people now to talk about the Floyd, Mana, Hoare approach. I mean, this is the formula, but we see the idea go back to Noor, McCarthy, and even Turing. And he said the paper attempts to provide an adequate basis for formal definition of the meanings of program in appropriately defined programming language. So now it's about the program, not about an algorithm. And again, you associate a proposition in connection with the flow control through the program. The proposition is asserted to hold whenever that condition is taken. Okay, so this is all about total correctness, but this point was not made clear yet. This is the first Turing Award citation where program verification is explicitly mentioned. So in his Turing Award citation, it says automatic program verification. It wasn't quite automatic, but program verification. And I think the culmination of that line of papers, it goes back to Tony Hoare paper in 1969, an axiomatic basis of computer programming, which is incredibly well cited. And again, in the Turing Award citation, this work was not mentioned, but this is the paper in which an attempt was made to explore the logical foundation of computer programming by use of techniques which were first applied in the study of geometry, axiomatic method, and later extended to other branches of science. But the paper goes beyond just, again, elaborating this idea, and it goes in both, I would say, in terms of vision and techniques. So in terms of vision, I think Hoare was the first to express what I call the program verification dream. And so here is a paragraph from the paper. When the correctness of a program, its compiler, and the hardware of the computer have all been established with a mathematical certainty, it will be possible to place great reliance on the results of the program and predict their property with a confidence limited only by the reliability of the electronics. So what Hoare is telling us that subject to the reliability of the electronics, we will have mathematical certainty of the correctness of the program. Mathematical certainty, this is a high bar, mathematical certainty. I will come back to that point, the dream of mathematical certainty. Hoare also gave us, of course, Hoare's logic. So now there is a formal logic for reasoning about program. This is what we call Hoare logic. We have the Hoare triples. You have the precondition, the statement, and the postcondition. And now you have various rules, for example, the rule of composition that essentially establish transitivity. We have the distinction between partial and total correctness, with and without termination. Completeness was left open, and it's a big subject area. When is Hoare logic complete? And I will not get into it. The answer is sometimes, but not always. Now, so this is 1969. Now we jump 10 years into 1979, and a paper appeared in Communication of the ACM, Social Processes and Proofs of Theorem and Programs by DeMillo, Lipton, and Perlis. And the paper basically says that the whole program verification enterprise is misguided. It is argued that formal verification of programs, no matter how obtained, will not play the same key role in the development of computer science and software engineering as proof do in mathematics. Further, the absence of continuity, the inevitability of change, and the complexity of specification of significantly many real programs make the formal verification process difficult to justify and manage. it is felt that the ease of formal verification should not dominate program language design. So this was basically says the whole program going, at that point it was 30 years old, because at 1979, May 1979, Turing was June 1949. This whole enterprise is misguided. As you can imagine, this was a fairly controversial paper, but it did make a very strong argument. And the argument was something which is a bit somewhat uncomfortable, which is, why do we accept mathematical theorems? And we say, well, there is a proof. Well, how do we know that the proof is correct? How does the community become convinced that the theorem and a proof are correct? And the argument was, at the end of the day, it's a social process. You show the proof to your colleagues, and they seems right. What about this? What about that? You give a talk. Think of Andrew Wiles giving a talk in the Newton Institute about his proof formula theorem. A gap he discovered. He works 2 years. He finds the gaps. Most of us believe that formula theorem has been proven. I doubt that anyone in this audience went through the proof. We trust the community. We trust the social process of the mathematical community. De Milo, Lipton, and Perlis argue that if you have a 1,000 pages mechanical proof of some very complicated program, nobody is really going to check it. Even the theorem is very, very long, and there will be no social process, so it will not be socially accepted. And without social acceptance, there's no trust. And we'll come back. The concept of trust or confidence is a thread that goes through this. Remember, Hoare promised us mathematical certainty. And the Milo, Lipton, and Perlis say mathematical certainty is achieved by a social process, which will not happen here. So we will not have mathematical confidence. That was the argument. As I mentioned, this was a very controversial article. There were follow-up. For example, there was a letter by Leslie Lamport later that year, and he said with the typical Lamport acerbic language, this paper made some excellent observations. However, by throwing in a few red herrings, they come to some wrong conclusions about program verification. More insidiously, they frame the debate as one between a reasonable engineering approach that completely ignores verification and a completely unrealistic view of verification advocated only by its most naive proponents. They're not saying exactly who are these naive proponents. We'll come back to that. Hoare did make a significant, Lamport did make significant contribution to program verification. Again, they are not mentioned in his Turing Award citation, which was really about distributed systems. There was another kind of philosophical argument that came a few years later against program verification, and this was by James Fetzer. And Fetzer makes a distinction between programs and algorithms. And he argues that algorithms are mathematical objects, and therefore you can talk about when we have an algorithm, you open any algorithms book, and you have an algorithm and a proof that the algorithm is correct. So algorithms are mathematical objects, you can prove them. Programs, he says, are engineering artifacts. It does not make sense to apply logical rule to engineering artifacts. You can test them, but you cannot prove them. That was the argument. He said, again, if you look at civil engineers, they have blueprints, they have a mathematical model they analyze, but the bridge, when you build the bridge itself is never verified. The model is verified, not the bridge itself. So he said we should make a distinction between the mathematical model and the engineering artifact. And I'll come back later to this point. Now, interestingly, while this, remember that De Milo, Lipton, and Perlis is 79, and Fetzer is 83, there is another development that is being ignored here completely, and this is the Pnueli's approach to the temporal logic of programs, in which he offered a unified approach to program verification, which apply both to sequential and parallel programs. And the main proof method suggested that of temporal reasoning, in which the time dependence of events is the basic concept. And he presents two formal system, one based on indeterminate assertion, one based on a temporal logic, which is particularly suitable for reasoning about concurrent systems. And in this case, this was his main, he got a Turing Award for his seminal work on introducing temporal logic into computing science for outstanding contribution to program and system verification. So very explicitly, his Turing Award was for program verification. I wrote the nomination letter, so it was, I know exactly what he's about. So, but Pnoeli's work would not have been recognized as such a significant contribution if it had not been followed by the model checking contribution. And this was independently by Clark and Emerson in 81 and Kane Sifakis in 82. Together they have, again, large number of citations. They are now, in this paper, they are giving effective procedures for verifying that finite set concurrent system meet specification expressed in branching time temporal logic. And they argue that we argue that this technique can provide a practical alternative to manual proof construction or the use of mechanical Turing prover for verifying many finite set concurrent systems. So on the one hand, I'll come back, on one hand, it's only finite state, but now it's algorithmic verification, as some people say. It's not manual proof, it's not computer-aided proof, it's a computer-generated proof completely. And Clark, Emerson, and Sifakis received the Turing Award in 2007 for model checking. Let me dig, since this is my own area, I want to dig a little deeper into what was the contribution here. So temporal logic was introduced by Arthur Norman Pryor in the 50s. And he was a philosopher. He was trying to think about free choice. But even he wrote in 67 there are practical gains to be had from these studies too, for example, in the representation of time delay in computer circuits. And a book that came in 1971 by Rescher and Urquhart wrote explicitly that there should be application to processes, a program sequence of state deterministic or stochastic. So what did Pnoeli do? Pnoeli took a logic that was developed before him, linear temporal logic, and he said, this is the right logic. This is basically propositional logic. At the time they had eventually always. Some other temporal connectives came later, the next and the until. And his argument was that in many programs, we need to specify not input-output relation, as Hoare does, but ongoing behavior. And the argument is that there are many programs that never terminate. They're supposed to run forever. Protocols, operating system, CPUs, they're supposed to run forever. And you reason about their ongoing behavior rather than about input-output relation. So linear temporal logic is propositional logic extended with temporal connective, next, eventually, always, until. The semantics is very, very simple. You reason about linear discrete traces, so it's a sequence of clock ticks. And next phi just said that in the next clock tick phi will be true. And phi until psi said that phi will be true in all the clock ticks until the clock tick where psi will be true, which must happen eventually. And so it turns out that these two connectives give us a very rich language. And in particular, you can specify safety and liveness properties. And the idea of safety and liveness was already described in Psalm 34:14, depart from evil and do good. So safety is depart from evil. Mutual exclusion is the canonical safety property. You say always not CS1 and CS2. You cannot be in two critical sections simultaneously. And liveness about some good thing must happen. For example, eventually request implies that always request implies eventually grant. If a request is made, it must be granted. And there are different request disciplines. For example, does the semaphore has to stay on until the request is granted? And then you say request implies that request stays on until it is granted. And so now you can describe in a very precise way different response disciplines. So I said the first kind of big bang in this area of temporal verification was Pnoeli's paper, the Introduced Temporal Logic. And then there are these two papers in 81, 82, and they look at the branching time logic called computational tree logic, or CTL. And they show that if you look at programs of size m, and what does size m here mean? These are finite set programs, so they have m states. And a formula of size n, you can do model checking in time that is multilinear. It is linear in both m and n. Pnoeli, even though he introduced branching time logic, was actually liked better linear time logic, and that's a whole other debate. We can spend here for an hour on that, but we won't now. And in a follow-up paper, he showed that you can do model checking of program of size m with respect to linear temporal logic formula of size n in time, which is linear in the program, but exponential in the formula. But they argued that programs are large and formulas are small, so this linear/exponential is practically reasonable. They use a method called tableau, which is borrowed from modal logic. My small contribution to this in this area, together with Pierre Wolper, was to go back to automata theoretic method, which were introduced originally for reasoning about logics in the 50s by Bushy, Elgot, and Trachtenbrot. And you could translate LTL to first order logic, and then use a classical result to translate to automata. But this would give you automata of non-elementary size. That is 2 to the 2 to the 2 to the 2 to the n, where the tower is of linear size. And what Pierre Wolper and I showed in some papers is that you can actually collapse all these towers, and you can do it in one exponential. Now, exponential sounds bad, but I'll come back to this point in a minute. But it turns out that this exponential translation gives us optimal algorithm for both satisfiability, which is p-space complete, and for model checking, we get the Pnueli-Lichtenstein result, but now using automata theoretic techniques. Now, the automata theoretic framework was elegant, but there were some doubts whether it was practical. So it took a whole decade to reduce it to practice. So optimized algorithm for model checking, symbolic algorithm, optimized explicit algorithm, how to compile it, how do you deal with the compilation? It's exponential, can you optimize it? Lots of work, lots of heuristics have done. And so I would say it's kind of by the mid 90s, it turned out that this mathematically elegant approach is also practically useful. And indeed, Bob Korshan has started building model checkers in the 80s. They were based on deterministic automata, and by the mid 90s, you can extend them now with LTL. Gerald Holtzman built spin, which is explicit state. Ken McMillan built SMV, which is symbolic states. And there was a fair amount of recognition. Brian Clark and Emerson McMillan received the Kanellakis Award in 1998. Holtzman received the ICM Software System Award for spin in 2001. And in 2005, Holtzman, Korshan, Pierre Wolper, and myself, we received the Kanellakis Award for this work. Now, interestingly, all this development is happening, and I think Tony Hoare was not much aware of it, because in 1995, in a workshop paper, he issues an apology, kind of an apology. 10 years ago, he writes, research in the formal method, and I was the most mistaken among them, predicted that the programming world would embrace with gratitude every assistance promised by formalization to solve the problem of reliability that arise when programs get large and more safety critical. Programs by now have got very large and very critical, well beyond the scale which can be comfortably tackled by formal methods. There have been many problems and failure, but these have nearly always been attributable to inadequate analysis of requirements or inadequate management control. It has turned out that the world just does not suffer significantly from the kind of problem that our research was originally intended to solve. So Hoare basically said it was a nice vision, but it was misguided. Amazing. 1995. But this was not very well known. In fact, I discovered this only when I gave a very early version of this talk, and somebody said, take a look at Wikipedia, at the Wikipedia article for Tony Hoare, you'll find his apology, and that's where I found a link to this apology. But the industry continued to accept formal verification, mostly for hardware, and I'll come back to that point. So IBM built rule-base, Intel built a tool called FormalCheck. They developed languages, Sugar and ForSpec, that led to standard industrial languages. PSL and SVA are IEEE standards, And today, if you go to the EDA industry, which is electronic design automation, the three big companies, Cadence, Metrographic, and Synopsys, each one of them has a formal verification tool, which is part of their suite of design tools. And this tool, I'm told by people that they are actually being used. I gave a talk last year at the Jasper user group, hundreds of people using these tools. Now remember, there was an issue of trust from the very beginning. Why do you verify programs so you can trust it? So model checking has the advantage that when it fails, it gives you a counterexample trace. And then you can go and analyze it. What was it? Was an error in the design? Maybe there was a bug in the specification. Maybe the model checker was buggy, but you have a counterexample you can analyze. Why would you trust when the model checker say yes? So it turns out that this is really the worry is, and your model checker said yes, and maybe you missed something. So the industry has developed various tests. For example, check your properties for validity. Maybe your property is always P implies Q or not Q. Now, of course, nobody would write such a stupid property, but maybe there are two Boolean expressions in the target, in the antecedent, in the consequent, that complement each other. So this property is always true because Q or not Q is always true. So check your property for validity. Also, there is a concept was evolved called vacuity. You can check that always P implies Q, and the model checker say yes, but if P never happens, then probably there is a mistake in the property or the program. So the industry has developed various sanity check. Why would you trust a positive result from a model checker? And it goes back to the same issue that at the end of the day, verification is about building confidence and trust. So let's quickly compare program verification versus model checking. Program verification is manual. It is expensive. It is long, slow, and agonizing. Model checking is algorithmic. You need the skill level that you need from the people who do is very different. People who do program verification, manual, usually people with PhD. People who do model checking, usually engineers. On the other hand, failure. When you have a failure of program verification, means you couldn't find a proof, but it doesn't give you a bug. You just couldn't find a proof. Model checking gives you a counterexample trace. And so it turned out that at least model checking is being more used. Some people call it computer-aided debugging. You find bugs very fast. In fact, sometimes some companies tell me they find bugs using model checking faster than they do using testing because it's much easier to get started. But the goals are different. Program verification is you want to ensure that the program meets the designer intent. That's a very high bar. Model checking is more modest. Give me some properties and I will check them. So the bottom line of model checking was do less, but do it better. And I think that's actually an important principle. You have sometimes you're trying to maybe climb the Everest and maybe it's too challenging. You say, let's climb the Kilimanjaro. It's still challenging, but not as difficult as the Everest. And then the industry has adopted it. So the level of automation, the possibility of doing modular verification, getting counterexample, IEEE standards, at least the hardware industry has adopted model checking. But it's clearly we are very far from Hoare's dream of mathematical certainty. But not everybody abandoned the dream. Other people continue to work on program verification according to Hoare's dream before he abandoned it in 1995. And the most famous of this work was the Boyer-Moore theorem prover. First it was called NQThem and then ACL2. And it was a proof assistant. You had to develop the proof manually and the software tool help you basically check the lemmas and the flow, and this is how it was done. It's a proof assistant engine. It's not a theorem prover per se. It's a mistake to call it theorem prover. But it does have many automated procedures. And one of the most impressive accomplishments was Warren Hunt, who was able to verify a microprocessor, the FM8501. It's not a real commercial microprocessor, but nevertheless, it was fully verified. And the industry has adopted it, and it's been used in a real application. And again, they received the ACM Software System Award in 2005. Now you see there have been more success in the hardware area, less in the software area. Why is that? Because for software, it's very easy to issue a patch, a new release. So if somebody tell you, oh, there was a bug, okay, we'll issue a patch, we'll fix the bug. How do you issue a patch for hardware? So there is some possibility, there are some ways of dealing with hardware errors and trying to mask them. But if you look what happened to the Intel with the Pentium 4 when there was the floating point division bug, it cost them $500 million to recall and basically tell you, if you have our chip, our CPU, we will replace it for you. And the estimation that today the world is much bigger. Today it would cost 10 times as much, maybe even much more than that. So this brings a whole new dimension to this. It's about the money. Money makes the world go round. So in fact, when you look, Microsoft started to invest in software model checking. When they realized they have a problem with the quality of third-party device drivers, their own bugs, they say they can issue patches and new releases to deal with their own bugs. They have a harder time with device driver. So they said, okay, we need to deal with software verification. So the big push for software verification started in Microsoft when they issued the SLAM with the software model checker. So how much verification to do is require cost-benefit analysis. Verification costs money. You have to decide if the confidence that you gain is worth the money. So at the end, it's not an academic decision. It's not an intellectual decision. It's a business decision. It's a business decision. And this is a thing, the idea this is a business decision. This is an insight that I think some of the visionaries from computing missed because they're not thinking in this way. But it's a business decision. And we'll come back to it. It's very important. It's a business decision. Now let's go back to the confidence. So remember, the Miller, Lipton, and Perlis made a very strong argument that we are going to lack social processes to accept proof. So should we accept proof by ACL2? Well, we have to accept the soundness of ACL2, and we have to check the assumptions. Assumptions have to be made explicit. But we can't say that if somebody has been proved by ACL2, you have to say, well, maybe the tool itself has bugs, and have all the assumptions are made explicit so we can trust them. So you have to believe ACL2, and you have to believe the people who did the verification. So there is some kind of a social process there. And so people have at least tried to address the issue of why should we believe theorem prover? If they are big beasts of software, they themselves may be buggy, and it's going to be very difficult to formally prove them. So people went back and thought, why do we trust mathematics? Why do we trust that ZFC, for example, we can reduce most of mathematics to ZFC? We know that we cannot prove in ZFC that ZFC is consistent, right? This is Gödel's second incompleteness theorem. But many people have looked at ZFC, and so far no one has found an inconsistency. So the idea is, let's build proof assistant with the small kernels, and all the proof must be extensible relative to that kernel within the formalism of the kernel itself. And the kernel should be small so we can subject the kernel to a social process. The kernel is not going to be 1,000 pages. We want the kernel to be at most thousands of lines. And we'll publish the kernel. And the whole community will read the kernel carefully and examine it. And so there will be a social process by this bootstrapping approach. And there are theorem proving such as HOA Light, Koch, and Isabel that follow this strategy. So the Miller, Lipton, and Perlis were right. You need a social process. They missed the fact that there is a way. There is a way we can build trust without people having to read, a 1,000-page mechanical proof. Now remember Fetzer's objection. The algorithm of mathematical object programs are engineering artifacts. Well, it's true. A mathematical is a mathematical object if it can be described with mathematical precision. How do we usually describe algorithms? We actually use a programming language to do it. I mean, there is no other way typically to write algorithm other than use some programming language. In fact, one of the criticism of, if you may remember, of the art of computer programming was the choice of programming language mixed to describe algorithms. So algorithms are really small programs. And it follows the distinction between algorithm program is somewhat artificial. It's a social distinction. Algorithms are what we put in a book because they're small, but they still have to be described in a programming language. So programs can be mathematical objects if they have mathematically defined meanings. So not all programming languages have mathematically defined meaning. C++, I think Fetzer is right. A program in C++ is going to be very, very difficult to verify formally because of the complexity of the language and the lack of formal semantics. C# was on the other hand, a variation with formal semantics, and Microsoft built a tool, Microsoft Research built a tool called SpecSharp that extends C# with a specification language feature and a theorem prover that you can do some formal verification relative to the language. And because the language has precise meaning, mathematically defined meaning, it makes sense. So, and in fact, we even have a model checker for C. And again, what is the meaning? The meaning in some sense is that there is a small compiler there, and the compiler is the meaning. And if it's small enough, you can examine it. And again, you can apply the social process. In this case, it's a bounded model checking tool that unrolls programs and translate them into logical assertions. And these are not huge programs. Again, people can examine them, and a social process can be built around it. And there was enough optimism that in the 2000s, Hoare has recovered from his momentary lapse in the 90s, but together with Jay Misra and Gary Levens and Shankar, they proposed the Verified Software Initiative. We propose an ambitious and long-term research program toward the construction of error-free software system. And they say in 15 years, we need a comprehensive theory of programming, a coherent tool set, a collection of realistic verified program. So 15 years will be in about 3 years. Are we going to get there yet? I don't quite know that they would have agreed that by 2024, their ambitious goal have been met. I think there was some progress, but maybe I don't think we can say, okay, we have fulfilled the 3 legs of the Verified Software Initiative. In fact, Microsoft Research announced in 2010 they will sponsor an award that recognizes significant technological advance towards the goal of the Verified Software Initiative. And they gave an award in 2011 and 2012 and 2013, and I can find no trace of any award after that. Somehow it fizzled out. But that is not to say there have been no progress in verified software. For example, an article from CSM in 2010 reported on an ambitious project on verifying formal verification of OS kernel, or microkernel actually. It was important to be a microkernel in Isabelle. So the microkernel was 8,700 lines of C and 600 lines of assembler. Okay, so because it's a microkernel, it's not a small program, but it's not humongous. And they were able to formally verify it. Okay, all the way to they had to make some assumption. They assumed the correctness of the compiler, of the assembly code, the hardware, the boot code. So it doesn't give you the mathematical certainty of that Hoare wanted, but it does give you much higher confidence in the kernel and how it will behave. And again, part of the assumption is that compiler bugs, so many people are using them that they will be caught otherwise. But it's not a mathematical certainty. And this is true for the hardware, for assembly code, for everything. There are bugs, but we don't have mathematical certainty. I'll come back to that point. And a few years later, in 2018, again, that the group of people went from proving formally verifying macrokernel to taking application, taking now an automatic pilot that runs over a microkernel, and now they have now they can assume the correctness of the microkernel, and they verified the code, the actual code of the automatic pilot. And one of the things they said is that you have to do some redesign and factoring, and partly not everything requires the highest confidence. You have to decide where should you put the higher effort, what level of security and assurance level do you need for which module? And because remember, verification is a business decision, and you have to decide where to put your money. And a project that will end this year, it was NSF expedition called Deep Spec, a 5-year expedition, headquartered at Princeton. It was launched in 2016. So, we will see if the usual expedition is it's a 5-year project, and large team, people from many institutions are involved, and they have wanted to take this work. They've basically said, we will take real software and develop detailed specification and prove all the way through that this is correct. And I encourage people that are interested to go and actually see what they have. They have really very impressive accomplishment, and you should go to their webpage and the paper they have written. And I would say this is probably, in terms of accomplishment, one of the high points. There are other that I don't mention. Again, I cannot try to be exhaustive here. And I think a very recent development that, again, it has to do with this mantra that I keep repeating: the verification is a business decision. The cloud is a game changer. Why is the cloud a game changer? Because now the scale is very, very different. And so also the issue of trust is much more important. So for example, imagine you're working at Amazon Web Services, AWS, and you want to convince, you go to Wall Street and you say, you should come and use our cloud instead of your own private cloud. And they will tell you, well, we are subject to regulation by SEC. And we have to be in compliance. We have various regulations that we have to comply with. And we have to ensure that we are in compliance of the regulations. So when we do our own private cloud, that's our own effort. Now we have to trust your cloud. Can we trust your cloud? So now the issue of trust is becoming not just it's nice to have, become a business imperative. We cannot convince people to move to the cloud unless we can convince them that they can trust that we are providing a high level of security. So provable security has become a cost-effective feature of AWS, because now if you are spending the money on security of some security feature, you are amortizing it over a huge business base. AWS is huge. I think I recently saw that maybe AWS is going to become bigger than IBM. Just AWS, not Amazon. Just AWS, I think, is going to either already or going to be soon bigger than IBM. So now the business case is changing because of the scale. So you can go and watch Werner Vogel, the CTO and vice president of Amazon, and he gave a talk at AWS reInvent 2020, where he explicitly said the automated reasoning group strengthen the foundation of AWS and provide the customer with tools to verify their own security posture. In 2019, just about a year before the pandemic, I visited the automated reasoning group in New York City, and we did a podcast on the history of verification. And I'm just blown away by the number. This podcast, which talks about program verification, has more than 150,000 downloads, which is just an unimaginable number for me. Again, other than the context of it's the cloud, it's part of AWS, it's part of their promotion that they are doing program verification, and it's a commercial feature now to do provable verification, to have provable security. So again, the cloud changes the business equation. And if we go back, that verification is a business decision, the cloud is a game changer. But the cloud is also a game changer in a different direction. So let's go back to before we go there, I'll come back to it, but let's go back to the dream, Tony Hoare's dream. Program verification dream, I would say 3 legs. We need to have great reliance, or we all accept that we should rely on the correctness of our programs. Confidence, yeah, that's a good idea. Mathematical certainty, this is what Hoare promised us. And I think it was what I would call a bridge too far. Great reliance, yes, it's realistic. We can try to increase reliance by using program verification techniques. Confidence, yes. mathematical certainty is a very fuzzy concept. As we saw, mathematical certainty is perhaps a social statement rather than somehow a technical statement. And the goal of mathematical theorem proving, when you prove a theorem in mathematics, your goal is to convince the mathematical community. The goal of program verification is to convince your customers, their user. It's just they're very, very different goals. And I think by somehow promising mathematical certainty, Hoare went, as I said, bridge too far, and this is not realistic and not attainable. And in fact, this is really what also Lamport already said in his 79 letter in response to the Miller, Lipton, and Perlis. Now, interestingly, however, the techniques that we develop for proof assistant has gone back to mathematics, because the mathematician has discovered they have some theorems where the proof have become so complicated they are really beyond human ability to digest, absorb, and say, yes, I'm convinced that this is true. And this is now many instances. One of the most famous was Poincaré's, when Poincaré's conjecture was proven about packing of balls. The proof was so complicated, the reviewer after 2 years says, we're not convinced. We cannot convince ourselves that this proof is sound and complete. And people have started taking back the techniques of a proof assistant and taking it with the kernel, with the extensible kernel, and they took it back to mathematics. And again, I encourage you to look at an article on formally verified mathematics by Avigad and Harrison from CSM in 2014, where they show that you can actually take computational proof assistant and go back and increase the reliability of mathematical claims. Because after all, in mathematics, we really want to have mathematical certainty. And actually, this is to me the ultimate irony for the counterpoint to the Miller, Lipton, and Perlis is that today we use a proof assistant to give us the mathematical certainty that the mathematician desires so much. But I mentioned the cloud gives us another problem, and this is vulnerability. And the big vulnerability that jumped in 2018 are the so-called Spectre and Meltdown. And essentially, what is Spectre? It turns out that today the x86 in particular, it does all kind of architecture to improve performance, and one of them is branch prediction and speculative execution. But in order that speculative execution leaves result private side effect that private data is revealed to attackers. How did you access memory? So it turns out that modern hardware x86. So x86 was really in a way to implement RISC in CISC. And one way they did it by using very sophisticated microarchitecture, branch prediction, pipelining, cache, a whole bunch of features, speculative execution, all kind of features that are very important to the performance. But however, they create a large gap between the logical model and the physical model. It make the physical model, it make the result from the physical model are revealed to an attacker. They provide a side channel. And the attempt, you can try to, once you know about a particular vulnerability, you can try to mask it. But one is you do it at the expense of performance. And what about the side channel that we have not discovered yet? So let me kind of conclude here that I think, maybe Tony Hoare's dream was, some parts of it were naive, but it was a very worthwhile dream. It did inspire a huge amount of research in computer science. We've seen the list of for example, I think the work on model checking would not have occurred without the program verification dream. Huge progress has been made. Much remains to be done. Mathematical certainty should not be the goal. Verification costs money, and the cost of verification should match its economic benefit. And so sometimes it makes sense to do model checking because that's good enough. Sometimes you want to do more and you do program verification. The cloud changes the cost-benefit trade-off. It creates massive scalability, So you amortize your expense over a much bigger computing base. So certain things that were not economical before become economical. So that's why AWS has automated reasoning group, because of this change in the cost benefit analysis. But shared hardware increases vulnerability. And the microarchitectural gap between the logical model and the physical model is a fatal weakness of x86. And I don't know that x86 can recover from that. There are other problems with x86, which is why people are predicting already as of last year, it faces obsolescence. It was an amazingly successful architecture. It's been running since the 70s, essentially, with several generations. But it's particular, I think the security gaps are something that this vision that people have, which is we will provide binary compatibility. The logical model will not change, but we will underneath improve the microarchitecture. That has proven to be a fatal error in terms of security. And finally, I will conclude that the focus so much has been on just on correctness and security. But now we have a bigger notion, a wider notion of trustworthy systems. And partly it is driven by the progress in machine learning. So while we have machine learning, now we have system with machine learning component. We train the, we have autonomous car, and part of it, there are some controller that are basically built by deep reinforcement learning. How do we verify functionality there? That's a very hot research area. But functionality is only one aspect. Remember, the goal is trust and confidence. And now our expectations have grown. We expect not only functionality, we expect fairness, lack of bias, we expect accountability, we expect transparency. So this conference FATE, that stood for fairness, equity, transparency, accountability, and added star because there could be other entities that could be added. So there are new challenges. We've made lots of progress, but the challenges are growing very, very fast. And I'll stop here, and I'm happy to have a discussion.
Thank you very much, Moshe. It's a great talk. We'll be automatically taken to the discussion room in 4 seconds, so we can take the questions there.
Okay.